reaction in this chapter is a little bit more involved. It's called Oxymercuration D-Mercuration. And it involves a type of an addition that we saw in the beginning of this chapter called anti-addition. If you recall, we did a little demo of anti-addition and syn addition. All right, notice too many N's on there. All right, so a couple things to look at. This is how you're going to recognize the reaction. You'll have some alkene, and you'll see reagents written above this arrow. So step 1 and 2, they're important. They're separate steps, so you have to carry them out separately. So it's important that you write 1 and 2 there. Other thing is that OAC thing here, that stands for acetate. So OAC equals acetate. All right, notice that we can use water here. That's what we use primarily in this chapter, or you could use an alcohol. Okay, and then you make an alcohol. So you get an alcohol, by the way, let's annotate this, from using H2O in step number 1. Okay, so that's what happens a lot in this chapter. But the other thing that we can do, right, we get this right, or we can get an ether. Okay, remember an ether is an ROR. We get that from using an alcohol in step number 1. Okay, but the mechanisms are going to be pretty similar to each other. All right, so let's take a look at the closer look at the two-step reaction. So the first part of this thing, I'm going to use a highlighter here, is we're going to have the oxymercuration. So it'll be hydroxy if we are adding an OH, or alkoxy if we're adding an R group. And we're going to get an HgOAC added anti to where the OH was. Okay, so that step we're going to spend a lot of time talking about. And then there's the second step, okay, and that is the demercuration. So we'll add a compound called NaBH4, sodium borohydride, and it'll replace the HgOAC with an H atom. Right, so it's Markov-Nikov orientation and anti-addition really occurring right here. And then this last little step we'll talk about in some more detail as we look over at the next page a little bit here. Okay, so there's a preliminary step down here below. Let's look at the mechanism, and let's look first, before we jump into that, I guess, at the preliminary step. So here's your Hg. Right, these guys are your OACs. So right, got 2 of those guys there. Okay. The first step that happens is you get acetate kind of just deciding to leave. It just kind of jumps off. It's not that bad. It's got resonance and stuff. And it leaves you with this little fellow right here. So that's what's going to react down below. Okay, it's going to be a positively charged mercury ion. Now, this reaction can occur at the top and the bottom. If you flip back to your notes where we filled this in the first page, these anti and syn additions can kind of do this top and this bottom attack. So I want to look at this molecule. So I got a methyl and an ethyl, and an ethyl and an H. And we're going to turn it over on its side, because remember, it's those p orbitals that we want to interact with. Okay, so when HgOAC comes in, we're going to see an electron flow where electrons come down here, just like so. Okay, and then the pi bond comes up to the mercury atom, right, just like so. I'll try to bend that thing around a little bit. All right, so that's your step number 1. Now what we get, and I'm going to draw this out with you guys a little bit slower. So you get your carbon, And you get your other carbon. Okay. The other substituents are going to stay where they were, so your ethyl's here, methyl's back, you got your H, and you got your ethyl right there. I just kind of want to show you, like up above, just a little side note up here. And so what kind of forms here is something that looks like this. So you get this little triangle essentially. Now that'll still have our groups over here, right? So still have your ethyl, your methyl, your H, and that was an ethyl, right? And then the Hg is attached to stuff, so it's HgOAC, and it has a positive charge on it still. Okay, now it turns out that you don't get this perfect looking isosceles triangle. So here's the idea, and this is important. We're going to see this in at least 2 more reactions in the next few pages. This is pulling electron density towards itself because it's electron deficient. So which side is it better to pull more electron density from? So in this case right now, you'd end up with, if it's perfectly an isosceles triangle, you'd get a delta plus here and a delta plus here that were equal to each other, right? But it turns out because you have an ethyl and a methyl group here, that you have a better chance at pulling a larger delta plus from that side. So we want a bigger delta plus there and a smaller delta plus on that side. And the consequence of that is it makes that mercury kind of lean a little bit. So down here below, we're going to draw it out like this. HgOAC with a plus, and we're going to do that. So you can see that I've slightly slanted it over to the right. And again, kind of putting that in, there's a bigger delta plus here, smaller delta plus there. So that's really important. So just to highlight that in writing, you have a larger delta plus here, right, because of those R groups attached to that carbon. Okay. So if we know that that's true, then it can help us out with the next step of this reaction. So the next step of this thing involves either the alcohol, right, or water here. So why don't we just use water, okay? So now water's your nucleophile. Which carbon is it going to be attracted to? Well, probably the one with the larger delta plus, right? So it's going to swing around here and attack from down below. Okay, and when it attacks right there, that's going to get plucked up to this position. Okay, so again, it's attracted to the carbon with the bigger delta plus. So that tells us the regiochemistry here. Now, it's going to leave us with our carbon atom and our carbon atom. All right, this fellow right here, that's not going to change. It's just going to kind of lean over. So that's going to be your HgOAC. Right? And it's going to have a set of electrons back on it so that it's content. The H and the ethyl group here, these two guys, they're not going to like flip or anything. They stay in their same relative positions. So you got your ethyl there, you got your H there. And the water's coming down below. So water's coming here to do this. Right? So we've seen that type of attack occur before in our substitution, our SN1. And then this ethyl and that methyl are going to get pushed up. So ethyl there, methyl there. And there we have it. And then the last step of this part 1, I'll come down here, is that we have water come over to do that final deprotonation. Okay? So Pretty straightforward step right there, but that's going to give us your carbon, carbon, HgOAC, right? Let you guys catch up in these positions. So again, right, that is anti. It's an anti-addition, right? And then we have our other groups just that we need to put in. So wedge and a dash at each carbon, and then we just copy them over, right? So ethyl front, methyl back, H front, ethyl back. All right, so that's what we get from this top attack. Now, there's no reason why the top is preferred. We could certainly add from the bottom. So let's take a look at the other approach. Right, now, the other approach is on the next page. So let's slide down here and let's take a look at this. All right, so coming through here, you got mercury coming down from the bottom, right? So double bond coming over here to the mercury atom, right? And coming up here to one of our carbons. So the same thing happens over here. We're going to get our, come up a little bit higher, going to get your carbon, your other carbon here. All right, now mercury is going to be hanging out closer to this carbon because that's the one that has the capability of, sorry, as I write this down, the other carbon is the one that bears the better delta plus charge, right? So it's going to come over here like this. So we get this guy. You can kind of see it's slightly leaning, right? And then OAC plus. All right, and again, remember the idea is that we have a bigger delta plus here, smaller delta plus over on that side. And then the rest of this reaction follows the same thing that we saw in the last step. So we added water before, so water is going to come over. Now it's going to come around here. It's going to attack on the top side and do that. And when we do that, we're going to end up forming our next intermediate. Right, so let's see if we can draw that out. So we start off with that. Take a second and draw that in. And we know something. So we know that that HgOAC should be here. Right? So it's just leaving. So that bond that's connected to this carbon right there, that shouldn't change. So that's right here. Right? The water that comes in is going to be in plane pointing up. So we know that. And here's the thing, if you know that, then the other groups just kind of stay where they were, right? So you got a wedge dash there. It's an ethyl and a methyl here. And over here you got an H and an ethyl pointing back. Okay? And then the last step of this thing is that deprotonation. So last step of part 1, bottom attack, coming around here, and we're doing this. Right, so I know it's kind of a lot, but once you write this thing out a few times, it's not so bad. So again, that's going to leave us with this. Right? Carbon, carbon, and then Hg, and I kind of ran out of space here. I'm going to write OAC. I think you guys know what I'm trying to do there. So get that in, and then get your wedges and dashes in there, and we're just copying down what we wrote before. So, right, we said that was an ethyl, we said this was a methyl, that's an H, and that's an ethyl back there. So we get this product. Now, again, this OH here and that HgOAC, these are anti to each other. Okay, so let's look at this example down below. So, you know, a lot of times we don't take the molecule and turn it on its side and do all that because we draw things in zigzags, right? Like this. That's what we do in OChem. So here's an example of our step number 1. So here, let's just imagine that we're adding HgOAC, right, plus, right, and then how about H2O here. So here's how you handle this type of situation when you're looking at a zigzag kind of a line here. So we know that the carbon-carbon double bond right here, we know that guy right there, that's going to react. So we're going to get 1, 2, 3, 4, 5, 6. Okay. Now we also know that the OH and the H need to be anti. Now that means a wedge-dash relationship in neighboring carbons. So down here below, we're going to start off at this carbon. That carbon is this fellow right there. So we're going to have here a methyl group pointing back, and then over here we're going to have to put an atom, right? And at this other carbon, we're also going to have a wedge and a dash. Now, what did we see before? We saw that the OH group, right, where does it go? It goes to the carbon that has more R groups on them. So that's this guy, right? That guy has a CH3 here, and then an ethyl group there. It's more substituted. So that's going to lead us with our OH group being at this position. Now, if the OH is there, then we need to put the HgOAC up here on a wedge. So HgOAC would go here. And then that guy's an H. Okay? So we can also do this from the other side. So again, we can come over here, right? If we came over here, the OH group could be pointing forward. And if that's pointing forward, then that Hg needs to be pointing back because that's anti, right? So what I'm circling here, these guys are anti to each other. Right here, right, coming out, the OH group coming out, the HgOC pointing back, and the H here, that's the other product that you get there. So the current relationship between these two guys, these guys are enantiomers of each other. That's how we're going to handle it in most of the problems that we see. We're not going to draw them out looking at the wedges and dashes like from this bottom kind of approach type of thing here. It's just time consuming to redraw things that way. All right, guys, so I want to look at this last little part. Last little step's pretty straightforward. So we'll end with this for our last step. So this is also important. This is a reduction reaction. So you're adding an H atom. That's when reduction occurs. And if you look what I've written down here below, I've just copied down what our products were from this top reaction. So, right, your OH is here, your HgOAC is here, and we use this compound called sodium borohydride. And it basically, we're not going to learn the mechanism of this thing, but what it does is it replaces the Hg with an H atom. Okay. So it just a side note on this, that replacement goes through a planar radical. So that carbon, if it was a stereocenter, could be racemized. So it turns out that, you know, as we look through this chapter and other examples, we typically don't see that because there's already one H here. So if you replace the other atom with an H, then this becomes a chiral. If it is chiral, then you would get this product with the OH here with an H on a wedge and dash. So this would become two products, right? Same thing down below here. You have your HgOAC. It's kind of going off to the left here, but that's replaced with an H. Now, because it's a radical, it could be either one of these guys. But again, it turns out to not be a huge issue as we go through this. All right, last little thing just to summarize down here below. Stereochemistry, we get this three-membered ring. And here's something else that I do want to point out to you. So we're going to see this happening a lot. So whenever you see that 3-membered ring, we get anti-addition. And we're going to see it like half a dozen times as we go throughout the rest of this semester. So 3-membered ring gives you anti. All right. The regiochemistry, H2O adds to the more substituted carbon of the cyclic intermediate because that has a larger delta plus charge. We kind of talked about above. Right? And because of that, that puts the HGOAC part, right, on the carbon with the most H's, which then eventually is replaced with a hydrogen atom, right? So that gives us the rich get richer, right, type of addition there.